Mechanical electrical analogies are the representation of mechanical systems as electrical networks. At first, such analogies were used in reverse to help explain electrical phenomena in familiar mechanical terms. However, as electrical network analysis matured, it was found that certain mechanical problems could more easily be solved through an electrical analogy. Theoretical developments in the electrical domain that were particularly useful were the representation of an electrical network as an abstract topological diagram, the circuit diagram, using the lumped element model, and the ability of network analysis to synthesize a network to meet a prescribed frequency function. However, the technique can be used to solve purely mechanical problems, and can also be extended into other, unrelated, energy domains. Nowadays, analysis by analogy is a standard design tool wherever more than one energy domain is involved. It has the major advantage that the entire system can be represented in a unified, coherent way. Electrical analogies are particularly used by transducer designers. By their nature they cross energy domains, and in control systems, whose sensors and actuators will typically be domain-crossing transducers. A given system being represented by an electrical analogy may conceivably have no electrical parts at all. For this reason, domain-neutral terminology is preferred when developing network diagrams for control systems. Mechanical electrical analogies are developed by finding relationships between variables in one domain that have a mathematical form identical to variables in the other domain. There is no one, unique way of doing this. Numerous analogies are theoretically possible, but there are two analogies that are widely used, the impedance analogy and the mobility analogy. The impedance analogy makes force and voltage analogous, while the mobility analogy makes force and current analogous. By itself, that is not enough to fully define the analogy. A second variable must be chosen. In the impedance analogy, for instance, this results in force and velocity being analogous to voltage and current respectively. Variations of these analogies are used for rotating mechanical systems, such as in electric motors. In the impedance analogy, instead of force, torque is made analogous to voltage. It is perfectly possible that both versions of the analogy are needed in, say, a system that includes rotating and reciprocating parts, in which case a force-torque analogy is required within the mechanical domain and a force-torque voltage analogy to the electrical domain. Another variation is required for acoustical systems. Here pressure and voltage are made analogous, impedance analogy. In the impedance analogy, the ratio of the power conjugate variables is always a quantity analogous to electrical impedance. The mobility analogy does not preserve this analogy between impedances across domains, but it does have another advantage over the impedance analogy. In the mobility analogy, the topology of networks is preserved. A mechanical network diagram has the same topology as its analogous electrical network diagram.